Hello everyone, welcome to One Stop Study Classes. We were discussing about relations and functions. In the earlier two classes, we covered ordered pairs, partition product, and relations. In this class, we'll discuss about functions. Now, if you have two sets, P and Q, with values as such, P is a set of two elements, 1 and 2, and Q is a set of three elements, A, B, and C. Then we know that number of P is equals to 2 in this case, and number of Q is equals to 3. P cross Q is partition product of P and Q. It will have 2 into 3, that is 6 elements. Any relation is a subset of P cross Q. In total, there can be 2 to the power 6 relations. This is total number of relations. Number of relations can be 2 to the power 6. Now, out of these relations, certain relations are called functions. We represent functions by small f. This relation is on P and Q, is on two sets P and Q, or relation from P to Q, because it is supposed to be an ordered pair. So this is represented by relation R from set P to set Q. If certain relation is a function, then it will be represented as function f from set P to set Q. It can also be written as function f colon P arrow Q, read in the same manner as function f from set P to set Q. If any two sets, if I represent these two sets in the form of arrow diagrams, and if I form a certain relation between them as such, this relation R is the set of two ordered pairs, 1, A and 2, B. This relation R has two elements, 1, A and 2, B, two ordered pairs. By observation, we can see that your domain is equals to first elements of the ordered pairs, which is 1 and 2. Range are the images or second elements of ordered pairs, which is A, B, and codomain is all the elements of Q, second set, which is A, B, B, C. By observation, your domain is equals to P, in this case of relation R. A is the image of 1 and B is the image of 2 based on the values of your relation R. This much we studied in the last class. By observation, we came to a conclusion domain is equals to P. By observation, we also understood that one image has only one first element. This first element of an image is called as a pre-image. So 1 is the pre-image of A. Similarly, 2 is the pre-image of B. So every image has only one pre-image and every pre-image has only one image. 1 is only connected to A and A is connected to 1, 2 is connected to B and B is connected to 2. A is the image of 1, 1 is the pre-image of A. and vice versa. So, from this observation, we can say that this relation is equal to function because it follows two rules. Now, what are those rules? One, your domain is equals to set P. Sure, domain is equals to set P. Second, no two distinct ordered pairs in F has the same first element. That means for a relation to be a function, apart from domain being equal to set P, you should not have two images having the same pre-image, or no two images should have the same pre-image. These are the two conditions. Here, as you can observe, no two images have the same pre-image. First pre-image is 1. 1 has only one image, A. It does not have any other image. 2 has only one image, B. It does not have any other image. In the same figure, or let's redraw it. In this particular example, I'm even changing the example for better understanding. Let's consider two sets A and B. A has elements 1, 2, 3, and 4. B has elements 1, 4, 9, 16, and 20, or 25. Now, let's form a relation. Let's have a relation. R is the relation between A and B such that you have 1, 1, 4, 3, 9, 4, 16. You have 4 elements over here of relation R, 4 ordered pairs. And each first element is unique. So your domain has 4 unique elements, 1, 2, 3, and 4, which is equivalent to your set P by observation, set A by observation. So the first condition is satisfied. The second condition states that no two images should have the same pre-image. Here, your images is range. Set of images is range. You have 1, 4, 9, and 16, 4 distinct images, and they are connected to distinct pre-images. So the second condition is also satisfied. This relation is a function. In the same figure, let's consider another relation. I'm representing it by a different color. So 1 to 1, 2 to 4, 3 to 9, and 3 to 25. So this relation R can be written as 1, 1, 2, 4, 3, 9, and 3, 25. By By observation, the first condition, is it satisfied? Here your domain is 1, 2, and 3, which is not equals to set P, because 4 is an element which belongs to P, but the same 4 does not belong to domain. So the first condition is not satisfied. How about the second condition? The second condition states that no two distinct images should have the same pre-image. 9 and 25 are two distinct images, but they have the same pre-image of 3. This is not allowed for functions. So if this condition is not satisfied, this condition persists that your two distinct elements have the same pre-image, then the function, then the relation is not a function. 9 and 25 are two distinct images with the same pre-image. This is not allowed. As the second condition is also not satisfied. Let's consider another example. One, 2, 3, 4. 1, 4, 9, 16, 25. Now, you have another relation. The relation R is 1, 1, 2, 4, 3, 4, and 4, 16. Here, your domain, first condition is domain, set of domain. 1, 2, 3, 4. The first 4 elements. So which is equivalent to set P, hence the first condition is satisfied. Second condition, observe 1, 4, 4, 16. Now these are two ordered pairs with same images, but this is not the condition. Our condition says two distinct ordered pairs should not have the same pre-image, same first element. So do you have the same first element in either of these scenarios? One, first domain, first element has only one particular ordered set. Second, first element has only one particular ordered set. Third may you have 3 and fourth may you have 4. So the second condition is also satisfied. That means no two images have the same image. Now, instead of these, if I would have had another relation, 1 to 1, 2 to 4, 3 to 16, that's it, with 3 elements, 1 to 1, 2 to 4, 3 to 16. This relation R has 3 elements. By observation, we can easily say that this does not satisfy the first condition, that your domain should be equal to for set P or A in this matter. Comma 16. Domain is equals to 1, 2, 3, which is not equals to your function f. Which is not equals to, sorry, your set A. So by default, your relation is not equals to function. But let's see if the second condition is satisfied or not. The second condition states that no two images should have the same pre-image. There are distinct pre-images over here. So by default, the second condition is satisfied because we have distinct pre-images. Always look out for repetition of pre-images. That is where you find your hint. If you have repetition in pre-images, you should see to it that they should have the same image. They should not have two distinct images. Now, this was a theoretical concept about functions. The functions, we are studying functions because it provides us new elements out of the same given elements. The same given elements were elements of the two sets A and B. A different combination. Sometimes sets, the functions, are also synonymously correlated with the words like map or mapping. They also mean functions. That means you're dealing with functions over here. Now, what is the practical relevance and why is this, does it see, if it seems like a complicated concept, it's not. And why are we studying functions now? We've already studied functions, but not in this respect, not the theoretical part of it, and not in relation with sets. So we've studied, let's consider an equation of straight line. Y is equals to x plus 1. A linear equation in two variable, equation of the straight line. So here we can say that y is a function of x. This kind of notation was already introduced to you, as well as the name of it, y is a function of x, introduced to you in 9th and 10th standard. But we did problems related to this kind of equation, rather than understand what exactly a function is. This is what we've just done. We've understood what exactly a function is. So y is f of x. For x is equals to 1, your y is equals to 2. Solving this equation. For x is equals to 2, y is equals to 3. For x is equals to 3, y is equals to 4. Now, if this were to represent to be represented in terms of function, your function would be written as f. F is a function such that from set x to set y, such that small x is an element of x and small y is an element of y. Here, what have we got? We can define this function in set builder form as an ordered pair of x comma y such that x belongs to capital X, small y belongs to capital Y. Okay, your domain is equals to capital X, and the next condition, no two distinct images should have the same pre-image. So your fourth condition. This is a function. In practical example, for different values of x, we get different values of y. But say you consider a value of y. Say you write these in this 1, 2, 2, 3, 3, 4. Or this can be y instead of y. We can also write it as x. So f of x. Would you want, in these conditions, the last condition states that no two images should have the same pre-image. No two distinct images should have the same pre-image. For one value of x, you have a unique value of y. When you put it in this equation, for x is equals to 2, would you want any value which is not equals to 3 if you place in this equation? No. For one value of x, you need one value, and unique value of y to be considered it in an equation. By relations, in the fourth statement, let's consider something like this: 1, 2, 2, 3, 2, 4, and 3, 4. What is happening over here? For x is equals to 2, you're getting y ki value as 3. For x is equal to 2, you're getting y as 4. But this is unexpected. This is unexpected. This is not required. Else, because if this exists, then this equation is not satisfied. Because for one equation, you can have only one value of y for one value of x. This here, what do you have? You have the same pre-image for two distinct images. And this is the second condition. Hence, they have written you should not have this condition. This is not required. No word is added over here. So, no two distinct images should have the same pre-image. Hope this is understood. So, this was practical relevance of functions. This was with respect to certain examples and its theoretical meaning. In the next class, we'll cover the rest of the chapter, and examples may be later on. Thank you.